In the next several lessons, we'll learn about special kinds of functions from a group to another group. And in preparation for that, we'll do an in-depth study of functions in general in this particular lesson. We'll look at what a function actually is, various components of a function, certain kinds of functions that will be useful in our study. So let's start with an example. Consider the function gamma, that's the Greek letter gamma, from z12 to z18, which is defined by gamma of a equals 6a for all inputs a and z12. And so here's a visual depiction of that function. If an input is a in z12, it gets mapped to or sent to 6a in z18. More concretely, if an input is 5, it gets mapped to 6 times 5 or 30 in z18, which reduces in z18 to 12. So symbolically, we would write gamma of 5 equals 6 times 5, which is 30, and that 30 is in z18, so we reduce it to 12. Now, here are several components of this particular function. First is the domain. The domain of this function is z12 because domain refers to the set of all possible inputs into the function. So here's the domain of our function gamma. Now what about z18? Well, that's the codomain of the function. So this set, z18, the codomain, contains all outputs and possibly other elements of the function. And we'll say more about that later in the lesson. And then the rule of our function is gamma of a equals 6a. Note here that the input a is in the domain z12, and the output gamma of a is in the codomain z18. Now please pause the video and work on day 15 classwork. Then afterwards, we will review some of the questions and concepts. In the classwork today, we looked at the function f from u35 to u35, where f of x equals 3x for all inputs x in u35. Now here, since the domain and codomain are the same, they're both u35, in these slides I color-coded it so that the domain u35 is represented in red, and the codomain u35 is drawn in blue or written in blue. So here's a claim that we worked on in the classwork. If a doesn't equal b, if these two inputs are different, then f of a doesn't equal f of b. The corresponding outputs are also different. So I like to go through a proof of this claim, but these not equal signs aren't usually easy to work with, and so let's instead prove it's contrapositive. Namely, if f of a equals f of b, then a equals b. And so we swap, then negate. So that's what we're going to prove. So we'll start with identifying our hypothesis and our conclusion. So that gives us the first and the last lines of the proof. So here's our very first line. Assume f of a equals f of b. And our very last line is thus a equals b. Now, f of a equals f of b translates to 3a equals 3b. And intuitively speaking, to get from 3a, oh, wrong color, 3a equals 3b to a equals b, we like to divide both sides by 3. Now, this is all happening in U35, so we can't divide by 3, but we can multiply by its multiplicative inverse, and that's what we're going to do. So we'll note that the multiplicative inverse of 3 is 12, because 3 times 12, 36 is 1 mod 35. And so we take this equation, multiply both sides by 12. And then we get 12 on both sides of this original equation. So we initially had 3a equals 3b, multiply both sides by 12, use the associative law to regroup, and then 12 times 3 both become 1 and 1, and therefore we have 1a equals 1b, thus a equals b. And so we just proved the claim. Well, rather we proved it's contrapositive, but therefore we can conclude that if a doesn't equal b, then f of a doesn't equal f of b. Now, what we just showed is that this function f is what's called a one-to-one function. And so let's generalize that idea in the next slide. We'll let f be a function from domain S to codomain T. And we say that f is one-to-one if it satisfies the following property right here. Namely, if a doesn't equal b, then f of a doesn't equal f of b for any pair of input a and b in domain S. In other words, in a one-to-one function, different inputs map to different outputs. So different inputs in domain S map to different outputs in codomain T. So if we're going to prove that a function f is one-to-one, here are the steps that we typically take. We first assume that f of a equals f of b, where a and b are in the domain S, and then we show that a equals b. And so this is essentially proving the contrapositive of our definition. So rather than working with this definition of one-to-one, in order to prove that f is one-to-one, we typically prove the contrapositive. So again, we assume that f of a equals f of b for a pair of inputs a and b, and then show that a equals b. Now here's another fact that we proved about our function f, namely, if y is in the codomain U35, then there exists some x in the domain U35 such that f of x equals y. And so the key here is that the element y in the codomain is chosen first. And so if someone hands you any element y in the codomain, then we have to show that we can produce some element x in the codomain that gets mapped to the given y. And so let's go through the proof of this particular claim. So we begin by assuming that an element y is in the codomain. Once again, that's important. We start with an element in the codomain, and then we must find an element x in the domain such that f of x equals y. So what could that x be? Well, we go to the function. Function is f of x equals 3x. In other words, we multiply any input element by 3. So if we're starting with an element in the codomain, then it seems like 1/3 y might be a good candidate, because if you plug 1/3 y into the function, it gets tripled, we end up with y. Now, we don't really have 1/3 here, but once again, we note that the multiplicative inverse of 3 is 12. So 12 is acting like 1/3 here. And so our candidate for x is 12y. Again, think of that as 1/3 y. And so we'll let x equals 12y. And so that's our input element that we'll use. Now, we have to actually verify that 12y is an element of U35. So why is that? Well, we know that x, or 12y, is in U35 because 12 is in U35 and y is in U35 because y was originally in U35, and U35 is closed under multiplication. So their product, namely 12y, must also be in U35. So now that we've found an element that we claim maps to y, let's actually go ahead and verify that. And so f of x is 3 times x, or 12y. Use the associative law to regroup. 3 times 12 is 1, and we're left with y. And therefore, we have indeed f of x equals y as desired. Now, what we just showed is that our function f is what's called an onto function. So let's generalize that concept in the next slide. So suppose we have a function f with domain S and codomain T. Then we say that f is onto if for every element little t in the codomain, there exists an element little s in the domain such that f of s equals t. In other words, s maps to t. So a way to think about this a little informally is that every element of the codomain gets hit by our function f. That's what it means for f to be onto. And I labeled these elements 1 and 2 because we choose our element t in the codomain first. For any element in here, then we can find an element in the domain that maps to it. So the codomain element must get chosen first. And then we have to find an element in the domain that maps to it. And so let's generalize what we did in the proof in the previous slide. Here are the steps to show that f is an onto function. So to show that f is onto, once again, we start with an element of the codomain. So we let little t be an element of the codomain capital T. In our example proof, we began with let y be an element of the codomain U35. And then the next step is that we must find s in the domain such that f of s is equal to t. And the key thing is that this s, little s, is usually expressed in terms of our element little t. So for instance, in our sample proof, we let x be 12y. Now, that was expressed in terms of our original codomain element. And then what we did in our example proof was we verified that this element s is actually in the domain. And so we verified in our sample proof that 12y is actually in the domain U35. Now this is only if necessary. Sometimes this element s is just so evidently in the domain that it's not worth showing, but I think in this case it was. We had to show that the product 12y is still in U35 because U35 is closed under multiplication. And then the very last step, I think of it as the I told you so step, namely actually check that f of s equals t. And so that's the very last step. Let's show that S satisfies the desired property, namely f of s equals t. And so that's typically a calculation. Once again, I think of that as the I told you so step. And so those are the steps needed to show that f is an onto function. And so in this lesson, we studied what a function is, what a one-to-one function is, and then what an onto function is. And we'll be using these concepts really throughout the remainder of this course. And so with that, this is the end of today's lesson, and I will see you next time.